Thanks, Arvinder, for inviting me to come here. Arvinder and I were graduate students together in Mumbai many years ago. So we have known each other for a long time. So it's a pleasure to come here, see the great new facilities that are being built here. And it's great to be in Arizona for the first time. I've never been to this state before. Okay, so Arvinder told me that there's not a whole lot of AMO physics here in the department, that I should aim at a fairly introductory level before I dive into my own results. So that's what I'm going to try to do. I'm going to give you a basic idea of what's involved in doing ultra-fast AMO measurements and why we want to do ultra-fast AMO measurements. And then I'll tell you a bit more about my own work. Yep. So like Arvinder said, the McDonald Lab is a large facility. We have typically about 10 faculty members doing AMO physics, somewhere between 5 to 10 postdocs, and maybe 20 graduate students. So a large group effort. I've been there almost 20 years now. So a lot of people have helped me do the work that I'm going to present. I just want to focus on some of them. So these are all formal graduate students. Varun Makhija led the rotational wave packet dynamics business in the beginning. That was the bulk of his PhD thesis. So you will not see his name very much because Hun Lam has taken over. The newer work has mostly been led by Hun. He was my graduate student, then continued as a postdoc in the department, and we moved him up to a research assistant professor recently because he's great and we are lucky to have him and we didn't want to let him go. Yeah, so these are the two primary drivers of the experiment that I'm going to talk about in my group. And I want to highlight three people in the department who do not directly work with me, but who have contributed significantly to the work that I'm going to talk about. Yep, and I have listed several people here, several faculty members at the McDonald Lab, some external collaborators that I've been fortunate to work with over the years. Okay, so here's the plan for the talk. I will begin with a fairly sort of general introduction to the idea of how we study molecular wave packets, what's involved, what's interesting. Then I will narrow down to looking at rotational wave packets. We control the rotational motion of molecules and what we can do by controlling the rotational motion of gas phase molecules. What can we learn by doing experiments like that? And then the third part of my talk would be what's called Coulomb explosion imaging. Yep. If you take a molecule, you strip the molecule of several electrons very quickly, you're left with a whole lot of positive charge, and the molecule just explodes. Yep. From grad school, my one-sentence introduction to what I do has always been shine a powerful laser on something, blow it apart, see what comes out, and this is exactly what we do. Right? We do Coulomb explosion of molecules by simply removing very quickly as many electrons as we can so that the molecule falls apart. And by looking at the energy and the momentum of the fragments that fall out, we can learn something about what the molecule was up to before we stripped it of the electrons. And I'll talk about how this helps us overcome what's called the curse of dimensionality. Right? Quantum mechanics becomes quickly more difficult to do as the number of dimensions in the problem goes up. And if experiments need to catch up, the dimensionality of experimental measurements need to grow as well. And this is one way to do it. Yeah, we can get many dimensional measurements by doing Coulomb explosion imaging. All right, so part one of the talk, I want to start with timescales of molecular motion and the Born-Oppenheimer approximation. So if you take a small molecule, I'm going to talk about molecules that have a few atoms, something like nitrogen or oxygen or sulfur dioxide. Typical timescales look like this. Rotations go from about 10 to 100 picoseconds. Yeah, where a picosecond is, oops. There we go. These buttons are really close together. A picosecond is 10 to the minus 12 seconds. Yep, vibrations are faster, basically because nuclei have less moving to do, so they can do it quicker. And vibrational motion takes place on 10 to 100 femtosecond timescales, a factor of 1,000 shorter. And electrons are lighter and move faster. And if you are here for Paul Corcom's colloquium, you would have learned that electronic motion is kind of limited in molecules to about 20 attoseconds. So 20 attoseconds and longer, depending upon the kind of electron motion you're looking at. So these are the timescales we are interested in. Yep. Modern lasers can give you light pulses, as Paul would have told you, that are comparable to that time scale. Yeah, you can get down to few tenths of attoseconds. You can make flashes of light in the extreme ultraviolet that are about that short. Okay, so like I promised you, basic quantum mechanics. Suppose you have a system, you start with its ground state, you shine some light on it and excite the molecule to an excited state, and you end up with what looks like a two-state wave packet, right? There are just two states. The laser pulse is gone. It's no longer being influenced by an external field. You end up with a two-state wave packet. You get the wave functions of the two states and these time and energy dependent phases, right? Basic introductory quantum mechanics business. Yep. And if you make a measurement of any property of this two-state wave packet, you will find that the time dependence depends on a frequency that's given by the energy difference between the two states, right? So that's the frequency that appears in the calculation of any observable in quantum mechanics. And it also depends on the relative phase. Yep. If you want to know for a quantum system that you don't understand very well what the energy difference is, you do a standard spectroscopy measurement. Yep. Shine some light, see what frequencies get absorbed. For a molecular system, that will tell you what the energy level differences is. This has been done since the birth of quantum mechanics, right? So this will give you the energy level difference. If you do a time resolved measurement, so you excite the wave packet, make a measurement as a function of time, and take the value of your measurement and do a Fourier transform, you can get both the frequency and the phase difference. These buttons are really close together. Yeah, let's see if I can, that doesn't work. Okay, you can get both the phase difference and the frequencies. Okay, the same idea generalizes to a wave packet of many different energy levels. Yep. So if you have many states instead of just two of them, the frequencies that you see in your spectrum is always the difference between the frequencies of two energy levels. So I've shown an example spectrum here. Yep. You can see several lines. This is a Fourier transform spectrum. I'll tell you briefly how we got the spectrum later on. Yep. And you can see a whole bunch of lines. And these lines correspond to energy level differences between rotational states of a molecule. Right. So this molecule it's an oxygen cation. It's in an excited state of the cation. It's not in the ground state of the cation. This molecule is spinning. Yeah. And that rotational energy gives, if you look at differences between neighboring energy levels, you get a series of energies. It's in a given electronic state, the B state of the cation, 4 different vibrational states, and we can identify exactly which vibrational states these are because we can measure the energy precisely enough. So we know which vibrational states we are in, we know which rotational states we are in. These are very sharp energy lines. Yep. Remember, a centimeter inverse is about, it's easier for me to remember. An electron volt is about 8,000 centimeter inverse. Yep. And we are looking at tens of centimeter inverse. Right? So these are milli-electron volt, micro electron volt scale. These are very precisely determined lines. So we know exactly what this is. Okay. So when you do a time resolved measurement, and if you can do a Fourier transform spectrum like this, you see a series of quantum beat frequencies. Yep. And since I promised Arvinder that I will do some things at the undergrad level, let me show you what that looks like for a classical observable. And I hope you can hear this and that the sound is not too annoying when I run this. So suppose I have 2 frequencies, one at 200 hertz and one at 201 hertz. Yep. And you can hear that classic undergraduate interference phenomenon of beat frequencies. Yep. Both the waves start in phase. So you get constructive interference between the 2 waves. Half a second later, because my beat frequency is a hertz, they're completely out of phase. You get interference that's destructive, the wave goes away, the sound amplitude goes down, and at a full second, one of those things have completed n cycles, the other wave has completed n plus 1 cycles, you're back to constructive interference, and you stop at that point. Yep. So this is, like I said, introductory undergraduate material. Yep. What happens if you have not just two, but let's say 20 different frequencies at the same time? Yep. And whatever you have in mind, you can compare with what that actually looks like and sounds like when I run this. So I'm going to use 20 frequencies separated by 1 hertz. I'm going to play them all at the same time, and yep, very quickly, those frequencies interfere destructively. The signal goes away, and it comes back up later at the end of a second, right? So instead of seeing a slowly modulated sound and a slowly modulated waveform, yep, the more tones you add to your spectrum, the faster the signal disappears. Okay, and it still reconstructs after a second because all the frequencies have come back and finished an integer number of cycles at the end. Yep. So the wave function or the oscillating function reconstructs itself at the end of a second. Yep. This is important for two different things. One, this is how we make at the beginning of our experimental chain really short pulses of light. Okay. Instead of having sound waves, we have electromagnetic waves coming out of a laser, and we ensure that we have a large number of frequencies separated by equal gaps, right? So they are all integer spaced. And instead of having just 20 tones, we have 100,000 plus frequencies all synchronized together. Yep. So the periodicity of a typical laser is on the order of 10 nanoseconds. Yep. The duration of the pulse that you get depends on how many tones you have synchronized. Yep. And if you have 100,000 of them, the duration of the pulse is basically the repetition rate divided by the number of tones. So you can get femtosecond pulses. Yep. Pulses that are coming out of a laser oscillator, only about 20, 30 femtoseconds long. Femto is, remember, 10 to the minus 15 seconds. Yep. So you can get these periodic pulses. They typically don't have much energy. You amplify them, and you can get powerful laser pulses that you can do a lot of things with. Right. So this is the foundation of these type of lasers are called mode lock lasers. Yep. Not only that, if you have a molecular system and you have a simple molecule like nitrogen and it's rotating, it turns out that the beat frequencies that you measure, energy level differences between rotational states of the molecule, are also integer spaced in exactly the same fashion. Okay. So you hit this molecule with a laser pulse, you excite many rotational states at the same time. They are all frequencies that are multiples of a single fundamental constant. They are all excited in phase. So the molecule produces a quantum wave packet that shows constructive interference between all the components of the wave packet at the beginning. Then the wave packet dephases. It looks like nothing is happening because you're sitting here in the middle. But after a fundamental period later, magically, apparently magically, the signal comes back on. Yeah, and we call these things quantum revivals. These things only happen because quantum mechanics says energies are quantized, and for simple systems, the quantization is an integer multiple of a fundamental constant. So this sort of behavior is common in quantum mechanical systems if the systems are simple enough. Yeah, more complex systems no longer have well-behaved energy levels, and you don't see this revival in quantum mechanical systems. Let me go back to my PowerPoint slides. And so this frequency spectrum corresponds to a molecule that is rotating. Yep. Right after the initial laser pulse excites this rotational spectrum, all the molecules line up in gas phase and point in the same direction. Yep. So you have a gas of molecules that are moving in independent directions with independent thermal velocities, but for a short period of time, they are all pointing the same way. So you have a collection of nitrogen molecules. They are far enough away with that they cannot talk to each other. Yeah, but the laser field puts them in a state where they all point in the same direction, then they rotate out of phase, and a full rotational period later, they've all rotated an integer number of cycles, come back together again, and you have a gas of molecules all pointing in the same direction again. Right? So this is a basic idea of how we do control of rotational wave packets. The idea that you always see beat frequencies is more general. Yeah, you always see beat frequencies in any quantum time-dependent measurement of any kind. Yes. Or can a molecule somebody have? So I'm looking only at the rotational motion of a simple linear molecule. If the molecule is more complicated, for example, this was the shape of my molecule, I can spin it like this, and I can spin it like this. These two modes will have different frequencies. So within a molecule, you can have multiple modes of rotation that will give you different frequencies. And the spectrum becomes a whole lot more complicated when you have more complicated molecules. Right? So you will still see frequency differences, but those frequency differences are no longer integer spaced for a more complicated molecule. So that experiment is typically done with a gas of molecules, so nitrogen gas, for example. So I have a whole collection of nitrogen molecules, but they're all nitrogen molecules, yeah, in the same electronic and vibrational state, and therefore their rotational spectrum is all the same. So if you have the same collection of molecules, but they are in different electronic states, and I'll come to that a little later, then you'll get slightly different rotational spectra. In fact, if you go back to this slide, yep, so you can see that it's not just one train of equally spaced frequencies that I have here. I have three different trains. Yep, and these correspond to the same electronic state, but three different vibrational states. Yep, so if your molecule is vibrating, its average bond length, it depends on how fast, how much it is vibrating. Yep, so as the vibrational energy goes up, the bond length increases a little bit. Yeah, and that changes the moment of inertia, that changes the frequency at which the molecule rotates, and that shifts my frequencies. And that shift is how I have identified which vibrational state I'm in. Yep, so I have enough resolution that I can tell the difference between V equals 3 and V equals 4. Yeah, there's sufficient shift. In fact, you can see that those lines are cleanly separated. They are not even overlapping here. This is V equals 4, V equals 3, V equals 2, or the other way around. Yep, V equals 4, the tall one is V equals 3, and the tiny one there is V equals 2. Yeah, and the lines are completely separated. You do see revivals in single molecules if you could do the measurement on a single molecule. Yeah, so every individual molecule is in this wave packet and it's undergoing this behavior. The measurements are not done on one molecule because you won't get enough information. The measurement is done on a lot of identically prepared molecules. Yep. Good question. So if you do not have an isotopically pure sample, you can tell. You can see because obviously the moment of inertia depends on the mass, and a sufficiently high resolution measurement will separate the isotopes. Yep, so we can do that. Yep, okay, let's go back. And here's what happens if you have a quantum system, which is what I've been talking about mostly. Yeah, I really like this website that allows you to do these things. And I think I can run the video, right? You think about the quantum wave packet as phasors at any point, yep, and the phasors rotate. And quantum mechanics says you can't see an absolute phase. The sum of the two frequencies goes away. Yeah, in the sound wave, you can hear the beat, the pitch of the beat note. Yeah, and you can hear its modulation. So you can measure both of those things. In quantum mechanics, the global frequency with which everything is oscillating cannot be measured. Yeah, it's an overall global phase. It cancels out, doesn't show up in any observable. So you can only measure the beat frequencies. You cannot measure the sum frequency in a quantum wave. Yep. So this website has lots of nice visualizations if anyone is interested in looking at those. So let's move on. The next one. Yep, I've already done this. I've shown you how this works. So okay, so that was a general thing. Yep. Suppose you want to look at an actual molecule and not just look at its rotation. Okay, remember the timescales of electronic motion is very fast. Vibrations is about a factor of 1,000 slower. Rotations is another factor of 1,000 slower. Yep. This allows us to simplify the problem of solving the Schrodinger equation because these things move at different time scales. And this fundamental idea is what lies behind what's called the Born-Oppenheimer approximation. Now, which basically says the electrons move so fast that if you move the nuclei, the electrons almost instantaneously adjust to the new positions of the nuclei. And the Born-Oppenheimer approximation says you can calculate what the electrons will do by freezing the position of the nuclei. So the nuclei not moving, calculating the energy level spectrum of the molecule. So you sit at some internuclear distance, let's say here, and you calculate the electronic spectrum of the molecule. Yeah, it gives you different electronic energy levels. And you do this independently for different values of the, you do this independently for different values of the internuclear distance, calculate an electron energy spectrum, connect all those points, and this gives you a potential energy curve or a potential energy surface depending upon how many dimensions you have. Yep. And then you think of the electrons determining the potential energy curve on which the nuclei move. Right? So the nucleus will move like a classical mechanics problem just converted to quantum mechanics on a potential energy well that looks like that. Right? So as the nuclei move on this surface, yeah, you're exchanging nuclear kinetic energy for electronic energy. Right? There's no gravity in this. It looks like a gravitational potential well. It's not gravitational potential well. It's just the energy of the electrons. Yeah, most of the time when we're thinking about molecular dynamics, we are thinking about it in this picture. The nuclei are moving and the electrons are continuously adjusting to the new position of the nuclei, which works great as long as the electrons are moving much faster than the nuclei are. Yep, that does not always happen. Okay, because remember, the time scale of any motion is determined by the energy gap between the states. The energy difference determines the frequency of oscillation if it's an oscillating thing. Yep, and it turns out that this electronic energy levels, electronic potential surfaces, yep, can get very close to each other. And if the potential energy surfaces get very close to each other, then the electrons in those two states, yeah, have electronic motion on a time scale that becomes comparable to the speed with which the nuclei move. And then the Born-Oppenheimer approximation goes out the window, and you can no longer think of nuclei as moving on potential surfaces determined by the electrons. That picture of separating nuclear motion from electronic motion fails. Yep. It turns out that this happens all the time, all over the place, as soon as you introduce any complexity in your molecule. Yep. Basic molecules like ground states of most molecules, you don't have to worry too much about this. As soon as you get to excited states, potential energy surfaces get very close to each other, Born-Oppenheimer approximation fails, and then you have to deal with what is called non-adiabatic dynamics. Right? The Born-Oppenheimer picture gives you adiabatic dynamics. That's relatively easy to calculate and often easy enough to measure as well. But non-adiabatic dynamics is harder to calculate. It's a multidimensional problem in which there are fewer degrees of freedom that you can ignore. Quantum mechanics is Schrodinger's equation is harder to solve. If you want to measure it experimentally, you have to follow dynamics on multiple dimensions at the same time. Yeah, otherwise you have an incomplete picture of what's going on. So there are various ways of measuring non-adiabatic dynamics. Yeah, but it's still a challenge. It's still a challenge to do the calculations. It's still a challenge to do the measurements. Yeah, so I'm going to show you one way of overcoming this problem of not having enough dimensions in your measurement and learning what non-adiabatic dynamics looks like. Okay, I've already actually talked about this. So if you have, my screen is showing something weird. Okay, if you excite two states within one electron, two vibrational states within one electronic state, yep, they share the electronic wave function. So the two-state wave packet can be separated into an electronic wave function and a two-state vibrational wave function. Yep, so the time dependence is now the difference between the vibrational energy levels. Yeah, and the electronic part of the wave function sits on the side, and it just looks like the nuclear wave packet is sloshing around in the electronic potential. This is our classic picture of what a vibrational wave packet looks like. Yep, and you will see energy levels differences that are determined entirely by vibrational energies, because the electronic energy gets cancelled out, goes away. Yeah, in a vibrational wave packet like this, you don't see the electronic energies. You only see the vibrational energies. Okay. All right. I talked about this. Let me skip that. Now, if you started with something like O2, oxygen, and you just add one more atom, life immediately becomes a whole lot more complicated. Okay. And this is a famously complicated, simple system, nitrogen dioxide. Yeah. It's a bent triatomic molecule. Yeah. If you're sitting here at the bottom near the ground, near the minimum of the ground state, yeah, there are no nearby potentials, and adiabatic dynamics, Born, Oppenheimer, everything works well. You get a nice, clean, well-behaved spectrum. You can describe the molecule as bending or doing asymmetric stretch and so on. Yeah, you get three normal modes. Everything works nicely. Okay. If you go to from the ground state straight up by absorbing a photon with about 3 eV of energy, yep, you already have a crossing between these surfaces here. Yep, and that completely destroys any regularity in the spectrum. Okay, you end up getting, if you do a high resolution measurement of the spectrum just below the dissociation limit, which is actually at this energy, about 3.1 eV, yep, you get a line density of about 10 lines per milli electron volt. Yeah, 10 energy levels in a milli electron volt window. And each of these states corresponds to a mixture of electronic motion, vibrational motion of three different kinds, rotational motion, spin is in the mix. You can't assign any nice properties to any of these states. Yeah. So even if you could find two states or a small number of states to excite, and you could watch a wave packet, you wouldn't be able to say what the molecule was doing in any normal language, right? Because you can't say it's vibrating, because it's not just vibrating. You can't say it's rotating, because it's not just rotating. It's doing all of these things at the same time. And the question becomes, how do you measure and understand a system like this? And what we do is not rely on frequency spectrum, right? Not rely on energy level differences, because they don't tell us very much. Instead, we launch a wave packet that involves a lot of these energies at the same time, yep, and we watch the molecule do whatever it is doing in real time, in the femtosecond time scale in which the molecule moves, in which the electrons move, in which the nuclei move, and we want to actually make a movie of what the molecule is doing. But if you want to do that, you have to be able to follow what the nuclei are doing. Yeah, take a picture, don't describe it. Just see what it is doing, right? Not separate different coordinates, which you can't do in this limit, right? So ideally, you would want a measurement that gives you a multidimensional picture as a function of time after the molecule has been excited to this wide spectrum of things that it can do. Yep, and we would like to be able to do that. Like I said, it's still experimentally challenging. There is no single experiment that can give you a picture of everything that's going on. So we rely on different kinds of experiments on the same molecular system to build a picture of what's going on. So you might do an electron diffraction measurement, you might do an X-ray diffraction measurement, you might do a photoelectron spectroscopy measurement, you might do a Coulomb explosion measurement, and then combine the knowledge gained from all of these things to build a picture of what's going on. Yep, I will talk about Coulomb explosion imaging. That's one of the examples that I'm going to show you. Okay, so to step back a little bit, if you're doing ultra-fast AMO physics, there are two broad categories of experiments that you can do. First one is the type that I've been talking about. You launch a wave packet, you don't disturb the system, you just watch it evolve. Yeah, so the interesting thing is, what does the molecule do after you have given it some energy and then just watch it do whatever it does? Yep. The other kind of experiment is, what does the molecule do? What do the electrons do while it is in the laser electric field? And if you're here for Paul Corcom's talk on attosecond physics, his talk was mostly interested in that kind of experiment. Yeah, attosecond physics involves controlling the motion of electrons in the oscillating electromagnetic field. Right, so that's what his talk focused on. I'm going to be more focused on the other column of experiments. Yeah, what does the molecule do after it has been excited and left alone, and how can we measure what it is doing? Yep. So I'll assume that you were here for Paul's talk. If you missed Paul's talk and came for mine, all I can say is, what were you thinking? So, all right. So a typical experiment looks like this. Yep. You send in a pump pulse, you excite a wave packet, and then you send in a second pulse that probes the system by some measurable. Yeah. And you do this using an interferometer. And the nice thing, of course, is that the speed of light is so large that you can move an interferometer by a small amount in a reasonably well-controlled fashion, microns, let us say, and the delay between the light pulses changes in femtoseconds. Right? So the fact that speed of light has a 10 to the 8 setting in it allows us to control time delays down to 10 to the minus 15 or even 10 to the minus 18 seconds. Right? The speed of light is a huge advantage for us. Right? So this is the type of experiments we'll do. Excite a wave packet using a pump pulse and then watch what it does using a probe pulse that generates our observable data. Yep. Measurements are typically destructive. So once you've seen it, the molecule is no longer in the wave packet that you want to observe. So what you do is rinse and repeat. Prepare another molecule in the same state, watch that one. Prepare another molecule in the same state and watch that one. When I say another molecule, typically it's not one molecule, although I will show you experiments where it is one molecule. Typically you have lots of molecules. They are essentially in the same quantum state. Yeah, because we start with cold molecules, we put them in the same quantum states. You're doing ensemble of measurements like quantum mechanics textbooks tell you to do the first time you go to a quantum mechanics class, right? So that's exactly what we do. Oops. So the McDonald lab. So Kansas State has a large group, as Arvinder and I already mentioned. I'll quickly tell you a little bit about that. The McDonald lab was initially funded as a collision physics lab. So we have an accelerator in the basement. Yeah, it looks a little bit like the compact XFEL lab, lots of radiation walls and 6 feet thick concrete walls and stuff like that. But it turned out that that sort of collision physics went out of fashion already in the 1990s. And in the early 2000s, the lab had decided that we don't want to do collision physics anymore, and we want to move to the hotter and more interesting at that point, and still field of ultra-fast AMO physics using lasers. We got our first femtosecond laser home built in 2001. Around 2004 or 2005, we had attosecond pulses in the lab. At that point, we had the second shortest attosecond pulses in the world. Yep. But the faculty member who was building that experiment moved on to greener pastures. So we stopped doing attoseconds for a while, and we recently hired a new faculty member, and we again have attosecond pulses. They are again the shortest in the world. So we are back in the attosecond business. So Meng Han is our new faculty hire who has just made some of the shortest attosecond pulses in the world. We typically have 8 to 10 tenure track faculty members, 1 or 2 research faculty members, technical staff of 3 or 4 people over the years. We have been continuously funded by the Department of Energy from the early 1970s, and some of you might remember that the Department of Energy came into existence in the mid 1970s. So we are older than the Department of Energy, right? So we have had continuous funding from that source since they came into existence. Yep. Some of the experiments that we are going to talk about, I'm going to talk about today, was done in collaboration with many of these people. I have put a red line around the 2 theorists we have on the team. Until last year, we had 4, and then 2 of them retired, and we haven't replaced them yet. So we'll hopefully build up and go back to a larger contingent of theorists in the team. Yep. Artem Rudenko, our current director, and Daniel Rolles and Uwe Thum have active collaborations with Arvinder, and I've collaborated with pretty much all of them over the years. Yep. So we have a fairly large program, lots of graduate students. You will find in ultra-fast AMO physics are graduates all over the place. Yep. All right. So with that quick introduction to what we do in the McDonald lab, right? So we do attosecond physics, we do wave packet, we do non-adiabatic dynamics, all kinds of cool stuff. Okay, so part 2 of my talk. I don't know how am I doing on time. Where is my? Okay, the rest of it I'm going to go fairly quickly because I just want to give you a flavor of the type of experiments we do in some detail and not dive into any particular experiment, right? So the first question I want to sort of address is, suppose you have a strong laser pulse, you remove an electron, you ionize it, the electron is gone. The question is, what state is the molecule left in and how would you know? Yep. So I'm going to show you some experiments that are related to what Paul told you about last time. Yeah. So if you have a strong electric field, remember, if you have a femtosecond pulse, you almost automatically have an intense laser pulse, right? Because the pulse duration goes in the denominator of the intensity, and the pulse duration is 10 to the minus 13 or 10 to the minus 14 seconds, right? So you automatically get a high intensity laser pulse. And if you put an atom in the system, yeah, you can do what's called multiphoton ionization. You absorb enough photons that the electron gains enough energy to escape the potential. Yep, you can actually absorb a few more photons because the pulse is so short and so intense. That's called above threshold ionization. If the intensity is large enough, you can think about the electric field as modulating the Coulomb potential of the atom. Yep. And when you combine the Coulomb potential, which looks like that, and the red and that dashed straight line, which is the laser electric field, which is uniform over that distance, you get this tilted potential barrier, and an electron which was bound here can tunnel through that barrier. Yeah, and this is called tunneling ionization. And this is what underlies all the harmonic generation from molecules that Paul Corkum talked to you about a few weeks ago. Yeah, and the point is, again, undergraduate quantum mechanics, tunneling is sensitively dependent on the width and the height of the barrier. So any electrons that are slightly more bound are much less likely to escape from the same barrier, right? So it's very sensitively dependent on what the intensity is. So for a long time, these laser pulses have been available, femtosecond laser pulses have been available since the 1980s. They became much more common in early 1990s. And now you can call up a company and say, send me a femtosecond laser. They will tell you what color do you want it in. Yeah, so you can easily get powerful lasers to do this. For nearly a couple of decades, it was believed that only the loosest bound electrons escape through tunnel ionization. Everything else contribution is very small. Yeah, and you do harmonic generation by taking the electron, driving it away from the atom, bringing it back, and when the electron recombines, it emits light, and that's how you get high frequency light, and that's how you get attosecond pulses. Yep. So the harmonic generation business was started back in the 1980s, and until 2008, it was believed even in molecules that only the loosest bound electron, the highest occupied molecular orbital, contributes to harmonic generation. And this experiment was done, the first one shown here, was done in Stanford. They controlled the direction of the electric field relative to the direction of the molecule. So if you have a nitrogen molecule and you can control which way it is pointing relative to the polarization of the laser, you can show that if you rotate the molecule, your contributions from HOMO, which is the weakest bound molecule, and the one that is just below it in the energy level, become comparable. So they were able to show that harmonic generation has contributions from HOMO -1 if you can control the orientation of the molecule to check that. Yep. A few years later, we were able to show that not only does the contribution from HOMO and HOMO -1 depend on the orientation of the molecule, the contribution from just one orbital, the HOMO, depends on the orientation of the molecule, because the probability that the electron will recombine with the molecule is a strong function of the orientation of the molecule relative to the incoming electron wave. Right? Both of these were done by being able to control the orientation of the molecule, which way the nitrogen atom was pointing relative to the laser polarization. And the way we do that is basically what happens to a compass needle in a magnetic field, right? It tries to line up with the local magnetic field. Yep, but that's not quite what we do, because we don't start with a magnetized, or in this case, an electric dipole moment. We use the electric field of the laser itself to produce the electric dipole moment. Yep. So when the laser is pointing up, oops, as it does here, it pulls the electron down to that end of the molecule, leaving positive charge on the other side. When the laser electric field flips direction, which happens in a few femtoseconds, yep, the electrons follow because the electrons can go across the molecule rapidly enough, and the direction of the torque does not change. Yep. So you end up with an effective potential that has a minimum at 0 degrees and 180 degrees, and the molecule will line up with the laser electric field polarization direction, just like a compass needle lines up with a magnetic field. Yep. You need to have a strong enough laser pulse to do this, but like I said, that's not hard to do anymore. Yep. The quantum mechanical picture, to rotate a molecule, you must give it angular momentum. And the way you get angular momentum, you remember each photon has 1 unit of angular momentum. You exchange photons in pairs. You absorb one, you re-emit another one, and keep all the angular momentum and give up most of the energy. So you only make a transition in the rotational level, which is very closely spaced in energy, but you gain angular momentum. So you climb up the ladder many times, and then if you go back to the spectrum that I showed you, this involves ladder climbing from 1 unit of angular momentum in the ground state of the molecule, and if you go to the other end, you've gone to 9 units of angular momentum in the molecule. Yeah, which requires interacting with, you have to basically steal angular momentum from 18 photons. So this molecule, just for climbing up the rotational ladder, had to interact with at least 18 photons. And this is the state of the cation, and you need at least 4 photons to get to the cationic state. Yeah, so this very nonlinear process, it requires the interaction with a large number of photons for you to be able to get a rotational wave packet that's broad and aligns sharply. Okay, this is how we typically do our experiments. We have a high pressure nozzle that we let gas expand into a vacuum system, and the adiabatic expansion of the gas cools it down. We get our molecules down to about 1 Kelvin, right? So these are cold molecules, not cold enough to be called ultra cold, but cold enough to be rotationally cold that we can essentially start with for a molecule like nitrogen, most of the population in the ground state of the molecule. Yep. And then we have some experimental tricks that I won't really go into. I do want to point out how we typically do our measurements. We have a spectrometer. Yep. So this is where the molecules interact with the laser beam. And the lines that you see are basically electrostatic plates. We put voltages on these things. We push the ions or electrons to a 2D avalanche detector. This is like a photomultiplier tube, except it's a many more channels. And then we can see, as a function of position, where our ion or electron landed on the detector. And we have a camera looking at the system, so we can take images. And this gives us a distribution of the momenta of the particles that we started with. Yep, we use something called a velocity map imaging spectrometer, which basically what it does is, when you take an image of the detector, the position on the detector where the particle landed is proportional to 2 components of the momentum of the particle. The third component is integrated over, right? So we have a 2-dimensional measurement of the momentum of every particle that hits the detector. Yep, and if you maintain cylindrical symmetry, that's enough to actually construct the full 3-dimensional distribution, because a cylindrically symmetric 3D distribution has only 2 degrees of freedom, and you haven't really lost any information. Okay, here's a measurement of nitrogen ions that we imaged. So at t equals 0, we hit the molecule, and the molecule is aligning, then losing alignment, going to the other side, and then coming back. And you see all these complicated distributions that show up and go away in the momentum distribution of the nitrogen ions. For a nitrogen molecule that we have impulsively aligned, so it's in a rotational wave packet, the molecules are spinning around, coming back into phase, falling out of phase, and it keeps repeating this over and over. Yep. Here's a measurement of the yield of oxygen plus singly charged molecule, and you can see it's modulated because the probability that you will ionize the molecule is a function of angle, and the angle is being modulated over time, yeah, by the rotational wave packet. Here's a measurement of a time-dependent yield from carbon dioxide, and you can write that as the probability density from the rotational wave packet times an angle-dependent ionization rate. So you get this convolution, and if you can solve the Schrodinger equation and determine the probability density, you can invert that and extract the angle-dependent ionization rate. So we know from this experiment that the carbon dioxide molecule is most likely to be ionized when it's pointing at 45 degrees to the laser polarization, and not at 0 degrees and not at 90 degrees. Yeah, and we can do this with fairly high resolution because we have very strongly aligned molecules in this experiment. We can extend this idea to rotations of more complicated molecules. So here's ethylene. Yep. Ethylene is an asymmetric top, and in 3 dimensions, you need 3 Euler angles to describe its orientation. In an axial asymmetric experiment, the azimuthal angle doesn't matter. So you're still left with 2 Euler angles, and we can extract the angle-dependent ionization rate as a function of 2 Euler angles. Yep. This is something you can't do using any other methods. Yeah? No other methods will give you this particular type of information. So we can use rotational wave packets, the fact that we can control the orientation of the molecule in space to learn about dynamics that we couldn't otherwise learn, right? In this case, for example, ionization. What's the probability that the ion is left in the ground state or the excited state when an electron is removed? And it depends on the orientation of the molecule relative to the laser polarization. Yep. All right. So the last part of my talk, I want to talk about non-adiabatic dynamics and how we can measure it, right? And this is the one that we do using Coulomb explosion imaging. We remove a bunch of electrons. In this case, we'll remove 3 electrons. The triatomic molecule breaks up into 3 pieces. We measure, in this experiment, all 3 momentum components of all 3 ions. So that's a 9-dimensional measurement. Yep. Momentum is conserved, so some of those things are not really independent, but still a multi-dimensional measurement of the momentum of the molecule. Okay, here's the molecule with which we did the first experiment, sulfur dioxide. If you start from the ground state of the molecule, and remove an electron so that you end up on the ground state of the cation, yeah, those potential energy surfaces are offset in the bending angle. Right? So the ion is born away from equilibrium in the ionic state, and then it executes bending motion like that. Okay? This you could have inferred just by looking at the photoionization spectrum, right? Because if you shine light of a sufficiently large energy, you remove electrons, you can measure the energy of the electrons. Energy conservation tells you what the energy of the cation is, and you can see this vibrational progression, and it's been known for decades that the cation is launched in a distribution of vibrational states of the bending mode of the molecule. Yep, and we wanted to see for this simple system of 3 atoms, if Coulomb explosion imaging, measuring the momentum of the oxygen and the sulfur will show us that the molecule is doing this over time. Yep, it takes about 85 femtoseconds for it to complete one bend. Yep, so you need to do this with sufficient time resolution that you can watch this molecule do this. Okay, so the experiment is slightly different from the one that I've told you before. We measure the momentum component of all 3 ions. We're going to focus on S plus, O plus, and O plus in a device called a Coltrim's device, yeah, which Arvinder tells me you're going to have here. You have here already, right? So this is fairly common, fairly sophisticated, but increasingly common way of measuring ion momentum. Yep. And I want to look at the momentum distribution of these 3 ions to be able to tell where the molecule was when the wave packet, when the electrons were removed and the molecules was basically forced to explode. Yep. And in fact, we can see that. So this was the first thing. Yep. If you plot the momentum of the sulfur ion and the momentum of the oxygen and the other oxygen ion, yeah, in this particular case, it turns out that the momentum distribution closely reflects what the molecule is doing directly. Yes? Yeah. No, in this experiment, we did not orient the molecules first. They have different masses. Yeah. And remember, the laser does not give the molecule any momentum. So the sum of the momenta of the 3 particles must be 0. Yeah. So you must get the 3 fragments from the same molecule. Otherwise, you just throw out that set of momentum because you know they came from different molecules. Yeah. So when you do these measurements in coincidence, things like momentum conservation allow you to guarantee that the 3 fragments that you're looking at came from the same molecule. Okay. So this experiment is done at an average rate of less than 1 molecule broken up per laser pulse. Yeah, so I told you usually we do experiments with many molecules at a time Cold rooms experiments are typically done with less than one molecule in the laser focus, or at least less than one molecule broken up by a laser pulse per laser pulse. Yep. And we can see this oscillating behavior with the correct frequency, yeah, corresponding to an 85 femtosecond pulse, as we expected. Yep. But there are several discrepancies between the model for this process that came out of the Schrodinger equation and a Coulomb explosion simulation and what we actually saw in the experiment. Yep. So the vibrational wave packet we can clearly see. We have the right frequency. The direct, simply take the momenta of all the particles and plot it, and you can see that the molecule is doing this, but not everything agrees. There are significant discrepancies between the calculated thing and the experimental measurement, even for a simple thing like this. Yep. And that's when we looked closely at what the molecule will do. Yep. And there are, first thing, everything depends on the orientation of the molecule. We are not controlling the orientation of the molecule in this experiment. Yep. But ionization, Coulomb explosion, excitation of vibrations, everything depends on the orientation of the molecule. For instance, the most polarizable axis of the molecule is the oxygen-oxygen axis, the A axis in this diagram. Right? There's an oxygen, sulfur. So when you shine light on it, the molecule will try, just like a compass needle, to make the OO axis line up with the laser polarization direction. So the first pulse, which ionizes this molecule, also forces it to rotate. Yeah, and rotational motion can be excited before the pulse is strong enough to ionize the molecule. So all these molecules start spinning. Okay. The second thing that matters, that the molecule likes to ionize most efficiently when the laser is pointing along the B axis. Right? So there's another angle dependent thing. Finally, the oxygen-oxygen sulfur channel that we are looking at is also angle dependent. It depends on where the molecule was. Right? So all these things are built into the time dependent measurement that we are making. And you can see, I won't go into the details, there are some features of this measurement that depend on the fact that the molecule is rotating. Right? So after the basic idea that the molecule is vibrating, you look carefully enough, you notice that the molecule is rotating at the same time, is doing both of those things. And the last thing we saw was that the same 800 nanometer pulse that we use for ionizing the molecule can also take the molecule from the ground state to the first excited state of the cation. Once it goes here to the top, it rolls downhill, and then you have two electronic energy levels that are very close to each other. Yeah, and your separation between vibrational motion and electronic motion is lost. Yeah, so as soon as the molecule is in the excited state, you no longer have clean separation between just vibration and rotation. Okay, and then you get non-adiabatic behavior. The molecule comes down here. Adiabatic behavior would have said it'll just roll over and go to the other side. Yeah, non-adiabatic behavior forces the molecule to go from the blue surface to the red surface and end up back on the bottom curve. It comes back to the electronic ground state. Yeah, it still has all the energy that absorbed from the laser, but it's back to the electronic ground state. If you plot this in 2D, the molecule starts here, goes down, ends up on the red surface, which is the lower, which is the ground state of the molecule. Yep, and quantum mechanics says that you can only do this, go from the blue surface to the red surface, yeah, by changing the electronic symmetry and launching asymmetric stretch motion. So the molecule starts doing this instead of just doing that. Okay, so you've gone from one type of vibrational motion to doing both of these, this and this simultaneously. Okay, and how do you know the molecule is doing this? Well, if the oxygen is close to the sulfur, it gets a lot of kinetic energy when you Coulomb explode it. The oxygen that's further away from the sulfur gets less kinetic energy, right? So the two oxygens that you measure from the molecule have asymmetric kinetic energy distributions, and that's exactly what we see, right? So this picture shows oxygen kinetic energy on one axis, the other oxygen kinetic energy on the other axis. You measure it where you don't expect to see asymmetric stretch, and it's on that diagonal. You measure it on this side at small angles. On small angles where you can only get if you go through this thing called the conical intersection at that point, non-adiabatic dynamics, and it clearly shows you that the molecule did this, right? So we can use Coulomb explosion. Now it tells us something about the electronic state. It tells us about the symmetry of the electronic state, which has now been mapped onto the symmetry of the vibrational motion. So Coulomb explosion dynamics, Coulomb explosion simulations tell us about this. Yep, so I'll skip the next one, which was a different molecule. There are challenges in Coulomb explosion imaging. We have been doing measurements with larger molecules, so you can see the momenta of many fragments at the same time. Multidimensional measurements, and of course, the thing to do these days is to use AI and machine learning to understand really multidimensional data. So we've been making progress on using AI and machine learning to understand the correlations in these many dimensional data sets. And with that, I'm going to stop. Yeah. So molecular dynamics in ultrafast laser pulses can be studied in a variety of ways and tell us exciting things that we couldn't have learned about molecules until very recently, right? Lots of technical development go in that are recent that allow us to do these things. With that, I'll stop and thank you for your attention.